Hello my dear students, welcome to the ACE Engineering Academy online platform. Dear friends, today we are going to discuss the most important questions and solutions for the most important subject for the mechanical engineers, that is thermal engineering. Dear friends, today's class is very useful for those students who are preparing for not only TSPSC AEE exam but also equal important for TSPSC AE exam, and also useful for the students who are preparing for AMVI. Of course, it is also useful for the APPSC AEE exam and AE exam. Okay? Dear friends, I am Malakondaiah Sir, faculty at ACE Engineering Academy. Dear friends, my hard work and more than 25 years of experience in the teaching field and blessings from parents and gurus elevated me to teach almost all thermal oriented subjects from the basic level to high end level. Dear students, we have divided the thermal engineering for TSPSC AEE exam into three parts, namely basic thermodynamics, power plant engineering and internal combustion engines, and refrigeration and air conditioning systems. Okay? Already I have explained the solutions for most expected questions for the first part on 20th of this month and the second part 24th of this month we have discussed. Today we are going to discuss the most expected questions for the very simple subject, that is refrigeration and air conditioning. Okay? Dear students, the subject refrigeration and air conditioning is very easy. That too, the syllabus is only three parts, namely air refrigeration cycles, vapor compression refrigeration cycles, and psychrometry. That's all. Only three topics included for the TSPSC AEE exam. Though it has only three topics, look at the weightage. Look at the weightage. In the year 2015, for the AEE exam, 8 marks were asked. Okay? The same year, the HMWSSB, that board also asked 8 marks, but the same board asked 10 marks in the year 2020. That is the weightage of this simple subject. Okay? Now, let us see the reference books, the best material for all the students, all the mechanical students who are preparing for TSPSC AEE and AE exam and also APPSC AEE exam is our academy material, that is ACE Engineering Academy material. This is the best material for both TSPSC and APPSC exams. Okay? In addition to this, you can also refer the other kind of material, that is objective question bank, mechanical engineering by a panel of experts, Aroma Publishing House, and one more material, the mechanical engineering objectives by D.S. Kumar. But I personally prefer our academy material for all state level exams. Okay? Now let us see the most expected questions for our subject. Look at the very first question. Try to read it. It is asked like this. In a Carnot refrigeration cycle, for constant upper temperature means higher temperature of the cycle remaining constant. As the lower temperature increases, option A, COP increases, B, COP decreases, option C, power consumption, just it is given just power consumption, D, heat transfer during the isothermal process decreases. Okay, as you know, the COP of the reversed Carnot cycle is depending on only two temperature limits, namely upper temperature is called highest absolute temperature and lowest absolute temperature TL. Okay, it is asked if lower temperature increases at constant upper temperature, what will happen in the COP? Okay, now if the TH is remaining constant, COP of the reversed Carnot cycle, एक minute, COP of the, I thought it is heat pump, reversed Carnot cycle is equal to lowest absolute temperature dividing by highest minus lowest absolute temperature. The previous problem I wrote is for COP of the heat pump, but it is asked for COP of the Carnot refrigerator. COP of Carnot refrigerator equal to lowest absolute temperature dividing by highest minus lowest absolute temperature. At constant highest absolute temperature, if the lowest absolute temperature increases, the numerator value increases. Because of the increase in TL, denominator value decreases. Therefore, the COP of the reversed Carnot cycle increases. Got that point? Once again, at constant highest absolute temperature, if the lowest absolute temperature is increased, the COP increases. Okay? Look at the option COP increases. The very first option itself is absolutely correct. Okay? Similarly, look at the another important question. Try to read it. In refrigeration system, the pressure between the evaporator and condenser equalize. You are asked to decide at what position of the refrigerator the evaporator pressure and condenser pressure are identical. Dear friends, remember, as long as the refrigerator is working, the condenser side pressure, that means refrigerant pressure in the condenser, always more than the refrigerant pressure in the evaporator. If I say the pressure of the refrigerant in the condenser is PC and the pressure of the refrigerant in the evaporator is PE, the pressure of the refrigerant in the condenser always more than that in the evaporator, as long as it is working. But it is asked in refrigeration system, the pressure between the evaporator and condenser will be equalized only when the system is not running. That means when you stop your domestic refrigerator, the refrigerant pressure may be equal in the evaporator location and condenser location. Okay? Look at the options. When the system stops functioning, yes, option A itself is absolutely correct. Only when the system is not functioning, the pressure of the refrigerant in the evaporator and pressure of the refrigerant in the condenser are identical. Okay? Similarly, Look at the another important question. Try to read it. Try to read it. On a particular time of a day, dry bulb temperature is equal to wet bulb temperature, then it can be safely concluded that it is given that in a particular day, dry bulb temperature is equal to wet bulb temperature. Dear friends, remember the dry bulb temperature and wet bulb temperature both will be equal only for saturated air. Of course, for a saturated air, dBT equal to WBT also equal to dew point temperature. Dry bulb temperature, wet bulb temperature and dew point temperature are identical for saturated air. Okay? For a saturated air, remember the relative humidity equal to 100%. Relative humidity is 100% and degree of saturation mu equal to 1. These are the conditions for a saturated air. Let me write it clearly. For a saturated air, एक minute, let me write it clearly. For a saturated air, these three temperatures are identical. Relative humidity is 100%, degree of saturation mu equal to 1. Now look at the options. Option A, specific humidity of the air is 0.01 kg per kg of dry air. No. B, dew point temperature was less than 20 degrees centigrade. You cannot say. Relative humidity of the air was 100%. Absolutely correct. For the saturated air, relative humidity is 100%. Okay? You know, if you take the psychrometric chart, the psychrometric chart is looking like this. This is how the psychrometric chart is looking. We are taking the dry bulb temperature on abscissa, specific humidity on the ordinate. This is the saturation curve. This is the saturation curve. Dear friends, remember, along the saturation curve, the relative humidity equal to 100%. Along the saturation curve, relative humidity is 100%. Okay? Along the saturation curve, dry bulb temperature, wet bulb temperature and dew point temperatures are identical. Okay? Then what is the wet bulb depression? As you know, wet bulb depression is the difference between dry bulb temperature and wet bulb temperature. For a saturated air, since dry bulb temperature and wet bulb temperature both are identical, therefore wet bulb depression is 0 for a saturated air. Okay? Anyhow, the option C is absolutely correct. Okay? Similarly, look at the another important question. Try to read it clearly. The preferred relative humidity in air conditioned space for human occupancy is asking the comfortable relative humidity. Preferred relative humidity for a perfect air conditioning units. Dear friends, remember, year-round comfortable conditions are year-round comfortable conditions or the temperature is from 18 to 25 degrees centigrade. That is the year-round comfortable temperature. The relative humidity from 50% to 60%. That is the relative humidity. And air velocity is from 3 to 8 meters per minute. These are the comfortable, that is year-round comfortable conditions. Temperature is from 18 to 25 degrees centigrade. The RH value means relative humidity from 50 to 60%, and air velocity is from 3 to 8 meters per minute, not second. Now look at the options. 30 no, 40 no, 50 to 60%. Yes, option C is absolutely correct. Option C is absolutely correct. Okay. Similarly, look at the another important question. Try to read it clearly. In a Bell-Coleman cycle refrigerant plant, compression and expansion of air are isentropic. For the Bell-Coleman cycle, you know, atmospheric air is the refrigerant. That too it is given compressor and expander are working by isentropically, means reversible adiabatically. If the temperature of the air entering and leaving the expander are 300 Kelvin and 180 Kelvin respectively, what is the COP of the plant? You are asked to decide the COP of the refrigeration plant when it is working on Bell-Coleman cycle with atmospheric air as the refrigerant. Okay. First let us see the Bell-Coleman cycle. As you know, the Bell-Coleman cycle consists of a compressor. This compressor is working by isentropically. Okay. Next, expander. It is clearly given that expander is also working by isentropically. Of course, this is the compressor. In between the compressor and expander, there is a cooler. Generally, cooler is constructed. This is a cooler. Cooler is constructed to work at constant pressure. And the cold chamber, this is the cold chamber. Cold chamber. Cold chamber. Cold chamber is the place where we are placing the working stuff. Where we are placing the working stuff is called cold chamber. That is your cold chamber. The cooler and cold chamber both are constructed to work at constant pressure. Now let me complete the cycle. This is the direction of the cycle. All refrigeration cycles must be constructed in the anti-clockwise direction. All refrigeration cycles must be constructed in the anti-clockwise direction. Okay. Now let us mark the state of the refrigerant. At the beginning of the compression is 1, where the pressure of the refrigerant is P1 and the temperature of the refrigerant is T1. Because of the compression, the pressure of the refrigerant may be increasing from P1 to P2. By that time, the temperature of the refrigerant is increasing from T1 to T2. Okay. In the cooler, some coolant is available. For that coolant, heat is rejecting at constant pressure. Okay. Because of the heat rejection in the cooler at constant pressure, just temperature is dropping from T2 to T3. It means pressure of the refrigerant at state 2 is P2 only. Okay, during the expansion process, definitely pressure of the refrigerant is dropping. Along with the pressure, temperature of the refrigerant is also dropping. Let the temperature of the refrigerant is dropping from T3 to T4, while the pressure of the refrigerant is dropping from P2 to P1, because the next process, constant pressure process, pressure after process must be equal to pressure before process. Okay? For this cycle, what is the COP? As you know, COP of the Bell-Coleman cycle, COP of the Bell-Coleman cycle is equal to 1 by RP, that is pressure ratio power gamma minus 1 by gamma minus 1. That is the standard formula for Bell-Coleman cycle when compression and expansion happening isentropically. Okay? But as you know, for the process 1 to 2, that is isentropic compression, for that process I can write that T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. Okay? This P2 by P1 only written as, that P2 by P1 is written as RP, that is called pressure ratio power gamma minus 1 by gamma, is equal to temperature after compression dividing by temperature before compression. Okay? Similarly, for the process 3 to 4 also, for the process 3 to 4, that is also isentropic process, isentropic expansion process. For that expansion process, I can write the temperature before expansion by temperature after expansion equal to pressure before expansion by pressure after expansion. T3 by T4 is equal to P2 by P1 power gamma minus 1 by gamma. Okay? This P2 by P1 we are calling as pressure ratio power gamma minus 1 by gamma is equal to T3 by T4. Now what is the T3? T3 by the temperature before expansion, T4 is the temperature after expansion. Okay? Now the COP of the Bell-Coleman cycle is equal to 1 by RP power gamma minus 1 by gamma minus 1. It is equal to 1 by, in place of RP power gamma minus 1 by gamma, I can write T3 by T4. Of course, you can also write that RP power gamma minus 1 by gamma, you can also write T2 by T1. But the reason why I selected the T3 by T4 in the place of RP power gamma minus 1 by gamma is the temperature before expansion given, temperature after expansion given. Okay? Now it can be also written as T4 by T3 minus T4. Okay? So let us see the temperature. If the temperature of the air entering and leaving the expander, temperature of the air entering the expander is 300 Kelvin and leaving is 180 Kelvin. So T3, this T3 is given 300 Kelvin and temperature after expansion given, temperature after expansion 180 Kelvin. 180 Kelvin. Okay? Now the COP of the Bell-Coleman cycle is equal to the temperature after expansion is 180 dividing by temperature before expansion is 300 minus 180. Simplify it. 180 dividing by 300 minus 180, 120. You simplify it, 0 cancelled. 6 3 are 6 2. It is 6 1 minute. Let me write it clearly. You should be very careful while You are solving the problems in the limited space. 6 3 ja 3 by 2. 3 by 2 is equal to 1.5. That is the COP of the Bell-Coleman cycle for the expander inlet temperature 300 Kelvin and outlet temperature 180 Kelvin. Understood clearly? Yes. Now look at the options. Look at the options. Option A itself is absolutely correct. Is it understood clearly? Yes. Now let us take the another important question. Try to read it clearly. Try to read it clearly. In aircraft refrigeration system, the refrigerant used is, dear friends, remember, air is the refrigerant for aircraft refrigeration. Once again, atmospheric air is the refrigerant for aircraft refrigeration. Option D is absolutely correct. Generally, the Freon 12 and Freon 22, these two refrigerants are preferable for vapor compression refrigeration system. Vapor compression refrigeration system. Freon 12 and Freon 22, those two are generally preferable for vapor compression refrigeration system. And dear friends, remember, oxygen is generally preferable for cryogenic refrigeration. Dear friends, cryogenic refrigeration means the method of artificially providing and maintaining up to minus 157 degrees centigrade is called refrigeration. The method of artificially providing and maintaining up to minus 157 degrees centigrade is called refrigeration. Below that minus 157 degrees centigrade is called cryogenics. Okay? For the cryogenic refrigeration system, we are using nitrogen, oxygen, hydrogen, helium, neon. These are the preferable refrigerants for cryogenic refrigeration. Cryogenic refrigeration is also called low temperature refrigeration. Practically, we are using the cryogenic range of temperature for storing the rocket fuels or rocket propellants. Anyhow, nitrogen, oxygen, hydrogen, helium, neon, these are all coming under low temperature range refrigerants, is also called cryogenic refrigerants. Anyhow, our question is, aircraft refrigeration system is working with air as the refrigerant. Okay? Similarly, look at the another important question. Try to read it clearly. In vapor compression cycle, subcooling of refrigerant before throttling. Dear friends, subcooling means the method of decreasing the temperature of the refrigerant below the saturation temperature by supplying some extra coolant to the condenser at constant pressure is called subcooling. Once again, the method of decreasing the temperature of the liquid refrigerant below saturation temperature by supplying some extra coolant to the condenser at constant pressure is called subcooling, is also called undercooling. Okay? Because of the subcooling, otherwise let me take the another slide. Effects of subcooling. Okay? Effects of subcooling refrigeration effect definitely increasing, but work required for compression remains constant. Okay. Then what about the COP? COP equal to refrigeration effect dividing by work input to the compressor. Because of the increase in refrigeration effect, at constant work of compression, definitely COP increases. Okay. Because of the subcooling, the coefficient of performance increases. Okay. Then what about the work required for the system? Work required for the system is equal to refrigeration effect by COP. Okay. Now if I want to get the same refrigeration effect, if I want to maintain the same refrigeration effect, for the same refrigeration effect, since COP maintained by vapor compression refrigeration system with subcooling is more, therefore work required for the same refrigeration effect can be reduced. There are two ways for deciding. Because of the subcooling, the COP increases. Because of the increase in refrigeration effect, COP increases. But if you want to maintain the same refrigeration effect, that means for the same refrigeration effect, because of the increase in COP, the work input for the compressor decreases. Okay. Now look at the options. Increases power consumption? No. Increases evaporator temperature? No. Reduces specific heat on? No. Reduces power consumption? Yes. Here reduces power consumption means for the same refrigeration effect. For the same refrigeration effect, definitely the power consumption decreases due to undercooling mechanism. Therefore, I am selecting the option D. Option D is absolutely correct. Are you following clearly? Yes. Now let us take the another important question. Try to read it clearly. Which of the following statements is correct? You are asked to decide the correct statement. During sensible cooling process, different options are given. Specific humidity will decrease, specific humidity will increase, relative humidity will increase. Option D, relative humidity will decrease. Because of the sensible cooling, let us see whether the specific humidity changing or relative humidity changing either in the positive direction or negative direction. For that, let us take the psychrometric chart. This is the saturation curve. Let me write it clearly. This is the saturation curve. Specific humidity is on ordinate, whereas dry bulb temperature on abscissa. Okay. Now, as you know, sensible cooling means the method of cooling the air at constant specific humidity. It is like this. Assume some air is flowing through the pipe. Air is entering and air is leaving. Air out. By the time the air is flowing from entrance to exit, assume we are connecting a cooling coil. This is the cooling coil. If I say cooling coil temperature Tc equal to some 16 degrees centigrade, the air is entering at 40 degrees centigrade. By the time the hot air is flowing over the cooling coil, its temperature may be dropping from 40 degrees centigrade to some 20 degrees centigrade. That kind of air cooling mechanism without change in specific humidity is called sensible cooling. Once again, the method of decreasing the dry bulb temperature of atmospheric air at constant specific humidity is called sensible cooling. That sensible cooling in the psychrometric chart can be marked like this. This is the representation of sensible cooling. During the sensible cooling process, specific humidity remains constant. During the sensible cooling process, specific humidity remains constant. Okay. Now, what about the relative humidity? Look at the state 2. Since the relative humidity along the saturation curve is 100%, state 2 is very close to saturation curve. The state 2 is very close to saturation curve. Therefore, the relative humidity maintained by the air at state 2 definitely high compared to the state 1 relative humidity. From that, you can conclude that because of the sensible cooling mechanism, relative humidity increases. Okay? The RH value, that is relative humidity corresponding to state 1, may be like this, RH1. This RH value corresponding to state 2. This RH2 curve is very close to saturation curve. Therefore, because of the sensible cooling, the relative humidity increases. Okay. Now look at the options. Relative humidity will increase because of the sensible cooling process. Therefore, I am selecting the option C. Understood? Yes. Now let us take the another important question. Try to read it clearly. Try to read it. A condenser of a refrigeration system rejects heat at a rate of 120 kilowatts. The heat rejected in the condenser given 120 kilowatts, while its compressor consumes a power of 30 kilowatts. The power consumed by the compressor or power consumed by the refrigeration system 30 kilowatts. The coefficient of performance of the system would be, you are asked to decide the COP of the system. Okay. What is the general formula for COP? Let me write here. The COP equal to ratio between the refrigeration effect and work input to the system. Okay. But refrigeration effect is not given. That refrigeration effect you need to decide from the heat rejection and power of the system. As you know, for any refrigeration system, the power input is equal to heat rejection minus heat absorption. The heat absorption is equal to heat rejection minus power input. What is the heat rejection? Heat rejection is 120 minus the power input is 30 is equal to 90 kilowatts. That is the heat absorbed by the refrigerant. Because of that heat absorption, the working stuff is cooled. Therefore, this heat absorption itself is the refrigeration effect. The heat absorption itself is the refrigeration effect. The refrigeration effect is 90 kilowatts. The power input itself is the compressor power 30. What is the value of 90 by 30? Definitely it is 3. Look at the option D. Option D is absolutely correct. Okay. Similarly, let us take the another important question. Try to read it clearly. Round the clock cooling of an apartment having a load of 300 megajoules per day. The cooling load given let me write it. Cooling load equal to 300 megajoules per day. Okay. Requires an air conditioning plant of capacity. Options given 1 ton, 5 tons, 10 tons, 100 tons like this. That means to maintain this much cooling load, what should be the capacity of the air conditioner required for that particular apartment. Okay. As you know, 1 ton refrigeration effect equal to 210 kilojoules per minute. That is the 1 ton refrigeration effect. Its physical meaning is, for removing 210 kilojoules of heat energy in 1 minute. For removing 210 kilojoules of heat energy in 1 minute, you can select the air conditioning unit of capacity 1 ton. 1 ton capacity air conditioning unit is sufficient for the removal of 210 kilojoules of heat energy in minute. Okay. But what should be the heat removed here? 300 megajoules per day. It is equal to 300 into 10 power 3 gives in kilojoules per day given. Let us convert from day to minute, because we have the value of 1 ton refrigeration effect equal to 210 kilojoules per minute. Okay. As you know, the number of hours per day 24 and 1 hour equal to 60 minutes. It gives in kilojoules per minute. That is the cooling load required. That is the cooling load required for that particular apartment. Now you simplify that value. If I simplify that value, it gives approximately 208 kilojoules per minute. How much amount of heat to be removed? From the apartment, 208 kilojoules of heat to be removed in 1 minute. For having the 210 kilojoules of heat removal in 1 minute, 1 ton capacity air conditioner is sufficient. Therefore, for removing 208 kilojoules of heat energy in 1 minute, 1 ton capacity air conditioner is sufficient. Therefore, you can opt the option A. Understood clearly? Yes. Now let us take the another important question. Try to read it clearly. A heat pump. Yes, this is the problem for heat pump. The heat pump working on reversed Carnot cycle has a COP of 5. Given that the COP of the heat pump is equal to 5. It works as a refrigerator taking 1 kilowatt of work input. The refrigerating effect will be the work input given. The work input is 1 kilowatt. Okay. As you know, the COP of the heat pump equal to 1 plus COP of the refrigerator. That is the relation between the COP of the heat pump and COP of the refrigerator. From that, the COP of the refrigerator is equal to COP of the heat pump minus 1. From that, you can conclude that COP of the refrigerator always less than COP of the heat pump by unity. That means, since COP of the heat pump is 5, definitely COP of the refrigerator is 4. Okay. What you are asked to find? You are asked to decide the refrigeration effect. It can be decided like this. As you know, the COP of the refrigerator is equal to refrigeration effect dividing by work input. Whereas COP of the heat pump equal to ratio between the heating effect and work input. Okay? Now from this, the refrigeration effect equal to COP of the refrigerator multiplied by work input to the refrigeration system. What is the COP of the refrigerator? COP of the refrigerator is 4 multiplied by work input is 1 kilowatt is equal to 4 kilowatts. That is the refrigeration effect of that particular unit. Look at the options 1, 2, 3, 4. Option D is absolutely correct. These are all very, very important problems for the APPSC AEE exam, APPSC AE exam, and also for TSPSC AEE AE and AMVI exams. Okay? Similarly, look at the another important question. Read it clearly. In a vapor compression refrigeration plant, the refrigerant leaves the evaporator at 195 kilojoules per kg. Refrigerant is leaving from the evaporator at 195 kilojoules per kg and condenser at 65 kilojoules per kg. Let me draw the pH diagram, pressure versus enthalpy coordinate system. With pH coordinate system, the saturation dome may be appearing like this. Dear students, remember the geometric shape of the saturation dome changing from one kind of coordinate mechanism to another kind of coordinate mechanism. Okay? With TS coordinate system, that is temperature versus entropy coordinate system, the same saturation dome is appearing like this. This is the geometric shape of the saturation dome with the temperature versus entropy coordinate system. The same saturation dome is appearing like this with pressure versus enthalpy coordinate system. Okay, understood? Yes. As you know, the vapor compression refrigeration system has only two pressure limits. Pressure before compression P1, of course that is also called evaporator pressure, and pressure after compression P2 is equal to condensation pressure or condenser pressure. If I assume the refrigerant is entering to compressor under dry saturation state, wherever the P1 line is meeting the saturated vapor curve, that is the state of the refrigerant at the beginning of the compression. The 1-2 process is the isentropic compression generally, 2-3 condensation, 3-4 throttling process where enthalpy of the refrigerant remains constant, but it is irreversible process. Since the 3-4 is throttling process is irreversible process. Thermodynamic sense for irreversible process is it should be marked with a broken line. It is like this. It should be drawn as a broken line. Okay? And 4-1 process is the evaporation process. Once again, 1-2 compression, 2-3 condensation happening at constant pressure, 3-4 throttling happening at constant enthalpy, 3-4 process you can also call as isenthalpic process, and 4-1 evaporation process where the pressure of the refrigerant remains constant. Understood clearly? Yes. Now let us mark the enthalpy limits. Enthalpy of the refrigerant at the beginning of the compression is H1. At the beginning of the compression means at the end of the evaporation, because this is the evaporation process. Evaporation process. This is the condensation process. And this is the compression. Compression process. This is the throttling process. Anyhow, H1 be the enthalpy of the refrigerant at the end of the evaporation. H2 be the enthalpy of the refrigerant after compression. H3 equal to H4. H3 equal to H4 is the enthalpy of the refrigerant at the end of the condensation. Enthalpy of the refrigerant at the end of the condensation is nothing but enthalpy of the refrigerant at the beginning of the evaporation. Understood? Now look at the enthalpies which are given. In a vapor compression refrigeration plant, the refrigerant leaves the evaporator. A refrigerant leaves the evaporator. Refrigerant is leaving the evaporator with H1 enthalpy. It means indirectly the H1 equal to 195 kilojoules per kg. Okay? Next. And the condenser at the refrigerant is leaving the condenser. The refrigerant is leaving the condenser means H3. Of course, H3 equal to H4. That H3 equal to H4, how much it is given? 65. 65 kilojoules per kg. So H3 equal to H4, 65 kilojoules per kg. Okay? For every kg of refrigerant, the plant can supply per second a cooling load. Cooling load means refrigeration effect. So refrigeration effect equal to mass flow rate of the refrigerant multiplied by refrigeration effect, which is in kilojoules per kg. Which is in kilojoules per kg. Here mass flow rate of the refrigerant is given for every kg. That means mass flow rate of refrigerant 1 kg per second. Here refrigeration effect. Refrigeration effect is nothing but the increase in enthalpy of the refrigerant during the evaporation process. The increase in enthalpy of the refrigerant during the evaporation is nothing but cooling effect H1 minus H4 is equal to H1 minus H3. Okay? H1 minus H3. H1 minus H3. It is equal to 1 multiplied by H1, 195 minus 65. You simplify this value. 195 minus 65 is equal to 130 kilowatts. That is the cooling load for this particular refrigeration unit. Now look at the option C. Option C is absolutely correct. Understood, no? Yes. Now look at the another important question. Try to read it clearly. Try to read it clearly. The COP of reversed Carnot cycle is 5. COP of reversed Carnot cycle is equal to 5. The ratio of the highest absolute temperature to the lowest absolute temperature. Let the highest absolute temperature is TH. Lowest absolute temperature is TL. This TH by TL is how much? Different options are given. Okay? Dear friends, as you know, the COP of the reversed Carnot cycle is equal to lowest absolute temperature by highest minus lowest absolute temperature. Isn't it? Yes. It can be also written as, let us dividing by TL on both sides, can also be written as 1 by TH by TL minus 1. Okay? Anyhow, COP of the reversed Carnot cycle, otherwise let me take the another slide. COP of the reversed Carnot cycle. How much it is given? COP of the reversed Carnot cycle is 5. 5. That is equal to 1 by TH by TL minus 1. Okay. From this I can write TH by TL minus 1 is equal to 1 by 5. Okay. What is the 1 by 5? Equal to 0.2. Therefore, the highest absolute temperature by lowest absolute temperature equal to 1.2. That is the answer. Okay. Try to get the answer. This is the answer. Option B is absolutely correct. Are you following? Yes. Similarly, look at the another important question. Try to read it. It is looking very big question. Try to read it. Subcooling heat exchanger is used in a refrigeration cycle. The enthalpies at condenser outlet and evaporator outlet are 75 and 182 kilojoules per kg respectively. The enthalpy at the outlet of isentropic compressor is 230 kilojoules per kg and enthalpy of subcooled liquid refrigerant 38 kilojoules per kg. The COP of the cycle is, different options are given. Okay. For this, better to project the pH diagram, pressure versus enthalpy diagram for your better understanding. Your understanding is very, very important. pH coordinate system. Let me mark the saturation dome. The saturation dome may be appearing like that. It consists of, it means vapor compression refrigeration system consists of only two pressure limits. Pressure before compression is also called evaporator pressure, and pressure after compression P2 is also called condensation pressure. Okay. For ideal vapor compression refrigeration system, ideal vapor compression refrigeration system means the refrigerant is entering to the compressor under dry saturation state. Got that point? Once again, ideal vapor compression refrigeration system means the refrigerant is entering to the compressor under dry saturation state. For that, wherever the P1 line is meeting the saturated vapor curve, that is the beginning of the compression. This is the state of the compression for ideal VCR cycle where the enthalpy is H1. Given that isentropic compression, 1 to 2 isentropic compression, after isentropic compression, look at the enthalpy of the refrigerant is H2. For the simple cycle, by the time the saturated vapor refrigerant is compressing, it is becoming superheated refrigerant. That superheated refrigerant is becoming saturated liquid refrigerant for the simple cycle. Means I am going to project the pH diagram without considering the subcooling effect first. Okay. So without subcooling effect, 3 to 4 is the irreversible adiabatic process, that is the throttling process, where enthalpy remains constant. And 4 to 1 be the evaporation process. 4 to 1 evaporation process. Okay. 1 to 2 isentropic compression, 2 to 3 constant pressure condensation, 3 to 4 constant enthalpy expansion. Generally we are using the capillary tube for throttling effect in our domestic refrigerator, water cooler and window AC unit, and 4 to 1 is the evaporation process happening at constant pressure. Okay. For this cycle, let me mark the enthalpy limits. Here it is H3 equal to H4. Let us see the enthalpy limits. Subcooling heat exchanger is used in a refrigeration cycle. The enthalpies at the condenser outlet and evaporator outlet. Condenser outlet. This is the condenser outlet. this H3 equal to, what is that H3? 78 kilojoules per kg, and evaporator outlet is 182. Evaporator outlet is 182 kilojoules per kg. That means indirectly, evaporator inlet enthalpy given, evaporator outlet enthalpy given. Okay? Similarly, the enthalpy at outlet of isentropic compression. Enthalpy at outlet of isentropic compression is H2 is 230 kilojoules. 230 kilojoules per kg. Okay. Now, let us see the subcooling mechanism. Subcooling means what? Method of further cooling the refrigerant. The method of further cooling the refrigerant below saturation temperature by supplying some extra coolant to the condenser at constant pressure is called subcooling. Once again, the method of further cooling the refrigerant below saturation temperature by supplying some extra coolant to the condenser at constant pressure is called subcooling. Okay? For the subcooling system, the throttling is happening at 3 dash ending at 4 dash, where the enthalpy H3 dash is equal to H4 dash. What is that enthalpy after subcooling? An enthalpy of subcooled liquid is 38 kilojoules per kg. This is 38. This is 38 kilojoules per kg. Okay? Now, COP for the simple cycle first. COP for the simple cycle is refrigeration effect dividing by work input. Work input. A refrigeration effect for the simple cycle is H1 minus H3. H1 minus H3 dividing by work input is enthalpy of the refrigerant after compression minus enthalpy of the refrigerant before compression. Because compressor is coming under a steady flow device. That too it is given compressor is working by reversible adiabatically. The reversible adiabatic steady flow work always equal to change in enthalpy of the working material. Therefore, work input to the compressor equal to enthalpy of the refrigerant after compression minus enthalpy of the refrigerant before compression, that is H2 minus H1. That is the COP of the simple vapor compression refrigeration system. But our cycle is subcooling cycle. The COP of subcooling refrigeration cycle equal to the original refrigeration effect RE dash dividing by work input. Work input cannot be changed. But what is changing? Refrigeration effect is changing. The new refrigeration effect with subcooling is H1 minus H3 dash. H1 minus H3 dash dividing by work input is same H2 minus H1. Is it understood? Yes. Now the H1. What is the H1 value? 182 minus H3 dash 38 dividing by the H2 230. 230 minus H1 182. You simplify this value. 182 minus 38. 182 minus 38. It is 144. So the numerator value is 144. 230 minus 182. 230 minus 182. Are you following? Yes. It is 8. It is 1248. 48. You simplify this value. This is the answer. 48 multiplied by 3, how much? 3, 24, 140. Yes. So it is equal to 48 3 times. Therefore, the COP equal to 3. The COP of the vapor compression refrigeration system with subcooling is 3. Look at the options. 3. Look at the option C. Option C is absolutely correct. Understood clearly? Yes. Similarly, look at the another important question. Try to read it clearly. Air conditioning has to be done for a hall whose RSH means room sensible heat. The room sensible heat is given 50 kilowatts. 50 kilowatts. And room latent heat also 50 kilowatts. Okay. Here room sensible heat and room latent heat both are identical. There are no other sources of heat addition or leakages. What is the value of RSHF? Means room sensible heat factor is how much? Okay. As you know, the room sensible heat factor is equal to ratio between the room sensible heat and room total heat. Room total heat. Room sensible heat dividing by room total heat is nothing but room sensible heat plus room latent heat. Room sensible heat plus room latent heat. It is equal to room sensible heat is 50 dividing by room total heat is 100 is how much? 0.5. That is the room sensible heat factor. Got that point? Look at the options. Option C is absolutely correct. Okay. Similarly, look at the next question. Try to read it clearly. Try to read it clearly. A Coleman air refrigeration system operates on which one of the following cycle? Option A, reversed diesel cycle. B, reversed Carnot cycle. Option C, reversed Brayton cycle. Option D, reversed Otto cycle. Dear friends, remember, the Coleman cycle is the reversed Brayton cycle. Of course, Brayton cycle can also be called as Joule cycle. Brayton cycle is the theoretical cycle for gas turbine power plant. Of course, Brayton cycle can also be called as Joule cycle. Once again, Brayton cycle or Joule cycle, otherwise let me write it. Brayton cycle, Brayton or Joule cycle is the theoretical cycle for gas turbine power plant. Gas turbine power plant. Gas turbine power plant. Like how the Rankine cycle is the theoretical cycle for the steam turbine power plant. Steam turbine power plant. Okay. Whereas the Otto cycle is the theoretical cycle for the practical petrol engine. Petrol engine can also be called as spark ignition engine. Similarly, diesel cycle is the theoretical cycle for the practical diesel engine. Anyhow, dear friends, remember, the reversed Brayton cycle is the Coleman cycle. Okay. So, reversed Brayton cycle is the gas refrigeration cycle. It consists of two isentropic process and two isobaric process. Look at the options. The Bell-Coleman cycle air refrigeration system is the reversed Brayton cycle or reversed Joule cycle. Following? Yes. Similarly, look at the another important question. Try to read it clearly. The inlet and outlet temperatures of air flowing over a heating coil having a temperature of 41 degrees centigrade. Let me mark the heating coil first. Assume the air is flowing like this. Air is flowing through a pipe. Air in and air out. Air out. By the time the air is flowing through a pipe, let me connect the heating coil. This is the heating coil. Okay. What is the temperature of the heating coil given? Temperature of the heating coil is 41 degrees centigrade. Once again, let me read it. The inlet and outlet temperatures of air flowing over a heating coil having temperature of 41 degrees centigrade. Coil temperature 41 degrees centigrade. Air inlet temperature 15 degrees centigrade, outlet temperature 28 degrees centigrade. Definitely, the dry bulb temperature of the air increases while it is made to flow over the heating coil. The dry bulb temperature of the air at the entrance is given 15 degrees centigrade and at the outlet given, let this is the state 1, this is the state 2, where the dry bulb temperature of the air is 28 degrees centigrade. Okay. Then what is the coil efficiency? You are asked to decide coil efficiency. Coil efficiency means heating coil efficiency. The heating coil efficiency equal to 1 minus bypass factor. That means you need to decide the bypass factor first. Okay. The bypass factor BPF is equal to this temperature difference dividing by this temperature difference. It means Tc minus T2 dividing by Tc minus T1. Let me write it clearly. Tc minus T2 dividing by Tc minus T1. What is the Tc? 41 minus T2 28 dividing by 41 minus T1 15. 41 minus 28, 31, 13 dividing by 41 minus 15, 26. Okay. What is the value of 13 by 26? 1 by 2 is equal to 0.5. I got the bypass factor 0.5. Therefore, heating coil efficiency 1 minus 0.5 is equal to 50%. Understood? Yes. Look at the options. Option B, absolutely correct. Understood? Yes. Similarly, let us take the another important question. Try to read it clearly. What is the commonly used refrigerant for domestic refrigerator? You are asked to decide commonly used refrigerant for our domestic refrigerator. Dear friends, remember, most preferably we are using the R12 as a refrigerant for our domestic refrigerator. Okay. Ammonia is generally used as a refrigerant for ice plants, cold storages, etc. Cold storages, etc. Okay. And carbon dioxide is generally used for marine refrigeration system. Okay. Anyhow, for our domestic refrigerator, generally R22 is the refrigerant. Understood? Yes. Similarly, look at the another important question. Try to read it clearly. The psychrometric process the air undergoes while passing through the desert cooler. You know, in the months of April, May, June, particularly in South India, the temperatures may be touching around 45 degrees centigrade. At that 45 degrees centigrade, our body does not feel comfortable. The common man is using a desert cooler. A common man is using a desert cooler for maintaining the low temperature in the room. You know the function of the desert cooler. By the time the air is flowing through the desert cooler, air is cooling and humidifying. That means cooling and humidification is the combination process with the desert cooler. The combination of cooling and humidification takes place by the time the air is flowing in the desert cooler. Therefore, option C can be selected. Okay? The cooling and humidification with psychrometric chart. Let us mark the cooling and humidification with psychrometric chart. This is the dry bulb temperature, specific humidity, this is the saturation curve. Saturation curve. Cooling means sensible cooling only. Let me mark separately. This is the representation of sensible cooling. 122 sensible cooling, 223 humidification, and 123 cooling and humidification. Let me write it clearly. 122 sensible cooling, 122 sensible cooling, 223 humidification. Humidification means method of adding the moisture to the atmospheric air at constant dry bulb temperature. Method of adding the moisture to the atmospheric air at constant dry bulb temperature is called humidification. So 223 is the humidification process. Humidification process. Okay. Whereas 123 is the combination of cooling and humidification. Understood? Yes. Anyhow, the desert coolers are maintaining cooling and humidification by the time the air is flowing through the three sides of the wetted pads. You know, around the three sides of the cooler that is having the wetted pads. By the time the air is flowing through the wetted pads, air is not only cooling but also humidifying. Means some moisture is added to the air. Understood? Yes. Similarly, look at the another important question. Hurry. 1 minute. Read the question. If mass of moist air in airtight vessel is heated to a higher temperature. If the air is heated in a closed vessel, what is happening? Different options are given. Specific humidity of the air increases, specific humidity of the air decreases, relative humidity of the air increases, relative humidity of the air decreases. For that, better to project the psychrometric chart. Psychrometric chart. This is the dry bulb temperature, specific humidity. Here air is heated. The heating process means sensible heating. The sensible heating process can be marked like this. Because of the sensible heating, the dry bulb temperature is increasing. Dry bulb temperature of the air is increasing from T1 to T2. But the sensible heating is happening at constant specific humidity. Okay, that means specific humidity remains constant during the sensible heating process. That is the representation of the sensible heating. Okay, look at the first option, specific humidity. No, specific humidity is not changing. During the sensible heating and sensible cooling, the specific humidity remains constant. Dear friends, remember, as long as the specific humidity remains constant, dew point temperature also remaining constant, because in the psychrometric chart, the horizontal line is giving the two values, specific humidity and dew point temperature. It is like this. The horizontal line in the psychrometric chart is giving specific humidity at its right end and dew point temperature at the left end. From that I can say that during the sensible heating process and sensible cooling process, not only specific humidity constant, but also dew point temperature remains constant. Okay. Anyhow, look at the relative humidity. You try to pass a curved line through state 2 representing the RH2 and curved line through state 1 representing the RH1. Is it RH1 curve closer to relative saturation? This is the saturation curve, right? This is the saturation curve. Is it RH1 curve is closer to the saturation curve or RH2? RH1 curve is closer to saturation curve. That means RH1 is more than RH2. I can write like this. RH2 is less than RH1. Because the curve which is far away from the saturation curve, the curved line which is passing through state 2 is far away from the saturation curve. Therefore, the relative humidity at state 2 is less than that of state 1. It means indirectly during the sensible heating process, the relative humidity decreases. The relative humidity of the air decreases. Therefore, you can select the option D. I hope all of you clearly understood. With this, my dear students, I am concluding the last part of thermal also. We have clearly discussed the most expected questions for the first part, that is basic thermodynamics, on the date 20th of this month, basic thermodynamics, and the 24th of this month, we have discussed the very important questions for power plant, and IC engines, internal combustion engines. Today we have discussed the most important questions for the refrigeration and air conditioning. With this, I am concluding the thermal part. Thank you. Have a great day. God bless you.